Hello and welcome to this fifth session. So we're starting here with an Olympiad question from 2009, I think it is, and it refers to some 2008 research on a Van Gogh painting. So in fact, using a non-invasive form of spectroscopy, it's possible to analyse pigments behind one of Van Gogh's paintings where he'd painted over an older painting. So a lovely context. The question starts off looking just at the hydrogen atom, the Rydberg equation we're familiar with there. So we're just looking here at the electrons in their shells, identified by the shell quantum number n. And then the question goes on to ask about the energy of an electron in hydrogen in electron volts. And so there we can see from the equation it's going to be a negative number, and so it's going to be minus the Rydberg constant, because z equals 1 and n equals 1, looking at that equation. So it tells us there that Rydberg is 13.6 electron volts. So the energy of the electron would be minus 13.6 electron volts, because of course we take the 0 to be the point where the electron is just ionized. And in fact, this is what they ask in the very next question. So in that multiple choice there, we're going for 0. And then finally it asks for the ionization energy of a hydrogen atom in kilojoules per mole. So in the stem of the question there, they give us the conversion for an electron volt into joules. They give us the Avogadro number. So in fact, multiplying this all up by the 13.6 electron volts, that will give us the ionization energy, or give us the electron energy in joules per mole, divide it by 1000, turn the minus into a positive, and we'll get the ionization energy of hydrogen. It comes out as 1312 kilojoules per mole. Now onto the second page of this question, quite a long question this, and so we're now looking really at the multi-electron atom context, and so this is why shielding comes up. So you remember that in the multi-electron situation we still use basically the hydrogen equation, so we're kind of adapting the one electron method, and rather than just having the atomic number for the charge on the nucleus, we're moderating it by subtracting a shielding constant, which takes into account the other electrons. And so the question part B here is about sodium and its ionization energy. And of course, ionizing sodium is going to involve removing an electron, the valence electron, from the 3s subshell. And that ionization energy is actually just going to be minus the energy of the electron, because the electron energy is a negative number. Because of course when we ionize it, we take it up to the level 0, energy 0. And so you see in the question it gives us the first ionization energy of 495.8 kilojoules per mole. And so what we're expected to do in this question is to call the energy of the electron minus 495.8 kilojoules per mole. For the Rydberg constant, we'd need to put in the kilojoules per mole value, so it'll be 1312 kilojoules per mole, because everything else is going to be dimensionless. We've got Z the atomic number, S the shielding constant, and N the shell number. And so what we're going to do in this case then is sub in the 495.8, or minus 495.8, the 1312 for the Rydberg. N will be equal to 3 for the valence electron, and so then we're just going to solve it for Z effective, which is what the Z minus S is on the numerator. That should be fairly straightforward. Then it gets more interesting. So then we move on then to the X-ray fluorescence part. And so there we go, we've got a real spectrum, that's good. And you can see some of the peaks here have been labelled K alpha and L alpha. And so there on the x-axis we've got these really high energies, and so you see on the y-axis it indicates these are X-rays. And then later on in the question it's going to explain to us what this K alpha and L alpha mean. So it says a peak marked K alpha is from a transition from 2p down to 1s. And so this is where there's like a hole in the 1s subshell where the X-rays radiation ionized a 1s electron, leaving a hole. And so then a 2p drops down into the 1s, and in dropping down in energy by conservation of energy, it then emits a photon of light E equals HF, giving you the frequency, and that's what's observed in this experiment and seen in the spectrum. And it says here, for such a transition, S is taken to be 1. So that's the S there in that earlier equation, the shielding constant. And so then in part C, it asks us to calculate the atomic number for an element which gives rise to the particular K alpha line in the spectrum. So we're going to have to read off the spectrum what the energy is, then putting that into the equation. We'll need to use the Rydberg constant in electron volts, won't we? Because the energy from the spectrum is in electron volts. And now, of course, in this particular case, this is a transition from the second shell to the first shell. So we're going to have to look at a difference between two energies. So you see we've got this n squared on the denominator. So we're going to have to consider n as 1 and n as 2 and subtract two terms. It'll be the difference between two energies. And then ultimately we're going to have to solve for the atomic number. So that Z minus S, that's going to become Z minus 1 because we're told in the question that the shielding constant S is 1. And actually the question goes on very much like this. It's a little bit repetitive actually. Because after this we go to the L alpha transition, which is from the 3D subshell down to 2p. So this is interesting because I think having booted out the 1s electron, a 2p has dropped down to 1s, and then it seems there's a vacancy in the 2p following that transition, causing a 3d then to drop down to the 2p. And so we're seeing all these lines in the spectrum. But because this is a different type of transition, we're going from a third shell to a second shell, obviously the shielding's all different, and we take S to be 7.4 in this case. And so in the next question it's a similar sort of thing, just different numbers. We've got different energy from the spectrum, we've got a different value for S, we've got different N's involved, but similar sort of idea. We just ultimately solve for Z to find the atomic number. And there are a couple of other bits and bobs in the question to do with the compounds that are these pigments. There's the sulfide coming up in D part 2, and then we've got another pigment, Scheele's green, E part 2. So I won't spend so much time looking at these pigments. We've got Naples yellow there at the end. But there you go, that's a bit of discussion about what's involved in the question. So what you might like to do is pause the video at this point, have a think about it, get as far as you can, and then come back to the video and I'll go through the answers with you. Right, here are the answers. I've just stuck them all up on this slide here. So we've looked at parts A and B already. Looking at part C now, you can see we've substituted the energy, 8,000 electron volts, into the equation. We've substituted 13.6 in for the Rydberg. We've substituted S equals 1 into the effective nuclear charge, so it's Z minus 1. And then in the brackets there, we're really subtracting the two terms, the two 1 over n squared terms. 1 over 1 squared minus 1 over 2 squared, corresponding to the second shell and the first shell. And so you can see in this equation the only unknown is Z. So you see we're solving for Z, and Z comes out as 29, atomic number 29. So copper evidently was the atom that was involved in this transition. So then going on to the next part, similar sort of thing, except this time it was 10,000 electron volts in the spectrum, and because it was one of those K alpha, no, it was L alpha, wasn't it, the L alpha transition, we had to substitute in S equals 7.4, so that's why you see that in the bracket there, Z minus S, it becomes Z minus 7.4, and because this was an electron dropping from the third shell to the second shell, that's why we've got 2 squared and 3 squared in the denominators in that bracket. So again we solve for Z, Z comes out as close to 80, 80 is the atomic number of mercury. So mercury was the metal in that particular pigment, and so mercury sulfide there is what it was ultimately. Then onto part E there, doing very similar sort of thing there for this K alpha and L alpha transitions. Similar sort of process, getting arsenic and lead coming out there, and therefore that formula in E part 2 dropping out, And finally in F there, that's looks like a slightly more straightforward one. Anyway, I think I won't spend too much time on these. I think we've got the main idea across there. So I think we'll just go on to the next slide at this point. Now I have to say there was something that really bugged me about this Van Gogh question that just looked really weird and wrong and just wound me up. And that was this idea that S equals 1 can be associated with one of these transitions. And in fact, we saw this was the case for the K alpha, and S was equal to 7.4 for the L alpha, equally bizarre. So why do I find this so bizarre? It's because when we were looking at Slater's rules, we found that these shielding constants we associate with a particular electron. But these transitions are not about the energy of an electron. They're about the energy of a transition, which actually, it's not even just the difference between two electron states either. Because remember, we said that when you get a transition like this, remember really you have to consider the entire electronic energy of the initial state, the entire electronic energy of the final state, where you're summing up all the electrons in the atom. Because of course when an electron moves, either from one shell to another, or if an electron's being ionized, that actually causes quite a lot of consequence, because these electrons will shield each other. So you can't really just consider an electron in isolation. This is what we found when we were looking at ionization last week. So it just seems wrong that a fluorescence can just be associated with just a single number for a shielding constant. This was really bugging me, and so I kind of resolved to try and get to the bottom of this. And I thought, well, let's try and kind of unpick this in terms of what Slater would predict about all the different shielding constants and how it reflects upon the fluorescence energy. So I kind of got stuck into this, and I thought, right, if we're going from a 2p down to a 1s, which orbitals are involved? So clearly all the orbitals in the first two shells are going to be affected by an electron moving from the second shell to the first shell. But actually there's more to it than that, because even the 3s and 3p subshells are going to be affected as well. Because if an electron drops from the second shell to the first shell, the shielding contribution from that electron is going to change. Because when that electron is in the 2p subshell, it's shielding the third shell electrons, 3s and 3p, 85% efficiently. But when that electron drops down to the first shell, into the 1s subshell, because it'll be two shells inside the 3s and 3p electrons, it will now be shielding 100% efficiently. So even those 3s and 3p electrons will notice the difference when this fluorescence happens. So really, to take into account all of these different transitions, all of these different energy changes, we're going to have to consider every electron in the first three shells. Now actually, when you are at least up to 3s and 3p, now if you go beyond that, the electrons from 3d and up, they won't notice the difference, because those outer electrons, for those ones, the transition will be so deep in the core that it makes no difference. It'll be perfect shielding either way. But we're going to have to consider all the electrons up to 3p. And so this is what I did, looking at this in a bit more detail. So taking each case, so each of these different electrons, what we'll need to do is to work out the energies. And so that will involve working out the shielding experienced by each of these electrons. And then we can drop that into our equation that involves the Z minus S, the effective nuclear charge. And so if we can sum up all of those electrons up to 3p in the initial state and the final state, then the difference between those two total energies should be the observed fluorescence energy. So this is what I've done here. It's quite a bit of work actually. You've got to sum over lots of different terms, and you might like to have a go at this, but equally if you just can't face it, you could just skip to the next slide and I'll go through the answer with you. So here we are, here are all the gory details. So first bullet point then, we're looking at the electron configuration 1s1 and then filling up the 2s and 2p. So this is where we have the hole in the first shell following the ejection of the 1s electron from the X-ray. So what I've done here in the next line is I've worked out the shielding constant, the shielding experienced by each of these different subshells. So for example, that single electron in the 1s subshell, that doesn't experience any shielding at all because it's the only electron in that 1s shell and it's not shielded by any of the outside shells. So that first S comes to 0. So you can see they're looking at the second shell. The S there is for each individual electron in that shell. So each individual electron will be shielded by the other 7 in that shell 35% efficiently. So that's multiplied by the 0.35. And then plus 0.85, that's the 85% efficient shielding from the one electron in the shell underneath. And then we've got the third shell electrons. So there's 8 electrons in the third shell. So for any one of those electrons, it's shielded by the other 7 in that shell 35% efficiently. That's the 7 times 0.35. Then the 8 electrons in the second shell underneath it will each shield 85% efficiently. That's the 8 times 0.85. And then the 1s electron, 2 shells underneath, that will shield 100% efficiently. So that adds 1 onto the shielding parameter. So there we go. We've got the shielding parameters there for the electrons in those first 3 shells up to 3p. So what I'll do in the next line there is we working out now the total energy. So that first term, minus z squared, this is for the electron in the 1s orbital. So remember it's z squared over n squared, so the n equals 1, and there's just the one electron, so it's no more than minus z squared. Then the next term is for the second shell. So the 8 there, that's because we're multiplying by 8 electrons that are in the second shell. We've got z minus s, we worked out that the s was 3.3, just above. And then z squared over n squared. So we're dividing by 2 squared because it's the second shell. That's the 4 in the denominator. Then we move on to the third shell. So the third shell has got 8 electrons in it, and that explains the 8 at the beginning. So we're multiplying up these single electron energy by 8. We worked out the shielding parameter there for the third shell to be 10.25. So we've got the z minus s there in the numerator divided by n squared. So n is 3. Square that gives you the 9 on the denominator. So that's our expression then for the total electron energy from 1s up to 3p on that initial state. And so you see with these z minus s squared terms, I've gone on to the next line there by simply expanding that out. And so that's giving us these sort of quadratics in z. And so I've expanded it out there, and I've tried to tidy it up a bit, and I've sort of factorised out 1/9, thinking that might help. So of course all these energies are negative, so I've got minus 1/9 times this expression that's quadratic in z. So that's all that work was done to work out the total energy from 1s up to 3p in that initial state. And then on the second bullet point, I do the whole lot again, except this time an electron has dropped from 2p down to 1s. That's why it's 1s2 there, and the 2p6 has now turned into 2p5. So it's very, very similar calculation, but some of the numbers change slightly, where we've got different numbers of electrons in different shells. So I won't go through all that lot again, it's the same as before. And so that gives us another expression that begins minus 1/9 and then a quadratic expression in z. So we've got the total electronic energy from 1s to 3p initially, and then in the final state. And so the difference between those two energies should be the observed energy in the spectrum, that fluorescence energy. So you can see that I've just simply subtracted one from another there. So you can see I've done, looking at the z squareds there, what have I done? You can see 41.75 z squared minus 35 z squared accounts for the 6.75 z squared, and likewise for the other terms. So there you go, I've got an energy there for that particular line what's that, the K alpha line, and I've got it as a function of Z, assuming that Slater's rules apply. Right, now having got that expression in terms of the Slater's rules, we now think about relating this to the expression given in the Olympiad question. Now in the Olympiad question, they described it in a much more simple way, where you simply had this shielding parameter S set to 1 in the question. That was just going to simply account for the whole transition. So we just had a kind of common S for both the initial state and the final state. And so what I've done here is I've simply plugged in the n numbers, the shell numbers, into the equation. So 1 over 2 squared minus 1 over 1 squared. That gives us this 3/4 that we can see in the final expression there. So that 3/4 z minus s squared is this very simple expression in the Van Gogh question for that transition. And so this little exercise I'm giving you now is saying, let's take a particular example of an element. So we've got an actual Z number we can substitute in. So let's take lead. I think lead was one of the elements that came up in the question. So lead is defined as Z equals 82. So if we take Z to be 82, we can substitute that in to our quadratic equation involving Z for the fluorescence energy using the Slater approach. And that should predict an actual energy using Slater's rules for the transition. And so what we're asked to do in this next exercise is to do this, and then using that energy and the expression above there from the Van Gogh question is to determine, in other words, using the Slater's rules to determine what that S ought to be, that shielding constant. So here we get to the end of this little task, and so that first bullet point there, this is the Slater energy we derived a couple of slides ago, which was this quadratic in Z, using, this is the end result of all those Slater's rules additions. And so there's our energy. So this is our energy measured in Rydbergs. So it's a massive energy actually, that's nearly 5,000 Rydbergs. So of course that's multiplied by 1,312 kilojoules per mole. And that's because I suppose we're looking deep into the core of the atom, where there's a gigantic nuclear charge. So there's sort of very, very large forces involved, hence these very large energies. And of course this is putting us out in the X-ray region, of course, where the energies are really large. There you go, so we've got a specific value there, nearly 5,000 Rydbergs for the transition. And so then what we're doing is we're now setting this equal to the expression from the question, where we've dropped in 82 into the Z. And then we now set these two equal to each other. So we're going to equate the Olympiad approximation from that question just in terms of the S. We're going to set it equal to the Slater energy we worked out. And so now we have an equation in which there's only one unknown, S. And it's a quadratic in S. And so if we solve that quadratic, the value for S that comes out is amazingly very close to 1, 0.998. So that tells us that when we work through all these Slater's rules, it actually does give this sort of S equals 1 idea some validity that we saw in the Van Gogh question. So that's brilliant. So that sort of neatly explains how our Slater's rules, if we work them through in sufficient detail, can explain these slightly bizarre looking shielding values that we were given for that Olympiad question. So doesn't that look nice? The only thing I should confess to is I've slightly cheated there, because I deviously worked out that actually, because we have this quadratic expression in Z for the Slater energy, it does mean that the agreement itself is going to be a function of Z. So actually the agreement is particularly good for lead, and if you took a much lighter element, the agreement wouldn't be quite as good. So I'm sort of slightly conning you there. So it's not always such a good agreement as I've just made out. But at least in that example, it does show you that it's quite good. In fact, if you take a much lighter element, the S is still over 0.9, so it's it's not wildly off. So the S equals 1 isn't a bad approximation at all. So it's quite nice how the Slater's rules can kind of justify this kind of shorthand method that we get in the question. I couldn't resist doing this with you really, especially as well if some of you might think it's all a bit inconsistent with what we did before with Slater's rules as well.